Welcome to the Explainer. Today we're going to tackle a super common Databricks problem, and we're going to do it by taking its really complex architecture and turning it into something we can all understand, a classroom.
You know the feeling, right? It's the question that drives every data engineer crazy. You write the code, you hit run, and then you just sit there, waiting. So let's figure out what's really going on under the hood.
Okay, so to get to the bottom of why things get so slow, we kind of have to start with the official Spark architecture. Now, don't get me wrong, it's super powerful, but yeah, as you're about to see, it can be a little intimidating.
So you look at this thing, you see drivers, executors, worker notes. It all feels really abstract, doesn't it? They tell you your job breaks into stages, and then those stages break into tasks. But what does any of that actually mean for the code you just spent hours writing? That's the real question.
Exactly. So what if we just thought about it differently? Let's just toss out all the technical jargon for a minute. We're going to build a really simple mental model that, I promise, is going to completely change how you think about writing Spark code.
All right, so here it is, our new model. I want you to picture a classroom, just a regular classroom. This room, this is your Spark cluster. It's where all the magic happens, and it's filled with students, all ready to get to work.
So in our classroom, the teacher is our driver. They're the one at the front of the room, planning the lesson, handing out the assignments. And all those students, those are your executor cores. They're the individual workers who are going to actually do the tasks.
Now this is super important. The teacher, our driver, doesn't get their hands dirty with the actual work. Nope, their job is to analyze the problem, create a smart plan to solve it, and then hand that plan out to the students. The teacher is really the brain of the whole operation.
And the executors? You can think of them like groups of desks in the classroom. Each group has a certain number of students, those are our cores, and they can all work on their assignments at the same time. So yeah, if the teacher is the brain, these students are absolutely the hands, carrying out the plan.
Okay, theory's cool, but let's put this classroom to work, right? We'll start with a really simple job that's absolutely perfect for doing things in parallel. Let's call it filtering candy. So, the teacher walks around and hands every single student a bag of candy. In the Spark world, each of these bags is what we call a data partition. The instructions are super simple. Just open your bag and take out all the brown pieces. That's it.
Okay, pay attention, because this is the most important part. Every student can do this job completely on their own. They don't need to talk to anyone else, right? What one student is doing with their bag of candy has absolutely zero effect on the student next to them. This is what we mean by a perfectly parallel operation.
And boom, just like that, the job's done. This is the dream scenario. This is the most efficient kind of operation you can have in Spark. It's what's technically called a narrow transformation. And it's super fast because there's no waiting around, no talking, no dependencies between any of our little student workers.
But you know, life's not always that easy, right? Not all tasks are that simple. So what happens when the students have to talk to each other? What happens when they need to coordinate? Now this is where things get really interesting. And it's exactly where those annoying performance bottlenecks start to pop up. Just think about it for a second. One student can't answer this question by themselves. They only know how many candies are in their bag. To get the grand total for the whole classroom, they're going to need to get the numbers from every other student. And this need for coordination, it changes the entire game.
But our teacher, the driver, is clever. They know how to break this problem down into smaller pieces. So first up, stage 1. The teacher gives a new task. Everybody, just count the number of pieces in your own bag. That's it. We'll call this the local count. And hey, look at that. Everyone can do this part in parallel again.
All right, stage 1 is done. Then comes stage 2. The teacher points to one student and says, okay, your job is to collect the numbers from everyone else. So that student goes around, gets a 5 from this person, a 6 from that person, a 4 over here, adds them all up and gets the final global count. And you see, that second step could only happen after the first one was totally finished. That line in the sand, that boundary between the everyone for themselves local count and the we need to work together global count, that is what defines a stage in Spark. Anytime your data has to be shuffled around or regrouped between your students, Spark has no choice but to create a brand new stage. And trust me, these stage boundaries, they're pretty much the #1 cause of slowdowns.
Okay, so let's bring this all back to the code we write every day. Let's see how our classroom analogy actually helps us.
Because this isn't just a fun little story. It's a surprisingly accurate picture of Spark's internal logic. In this slide just nails the connection. Look, on the left, you got our classroom with its 2 stages, local count, then global count, and on the right, that's a real diagram from Spark's Query Optimizer. It's not an analogy anymore. That 2-stage process is literally exactly how Spark plans and executes a count operation.
So who cares? Why does this matter? Well, it matters because now you can actually see your code in action in your head. When you type group by or join, you can picture all your students having to stop what they're doing, talk to each other, and shuffle all their papers around. You can finally get an intuitive feel for which operations are cheap, like our simple candy filtering, and which ones are expensive because they force everyone to stop and coordinate in a new stage.
So what are the big takeaways here? What should you actually do? Well, first, stick to data frames or SQL. This gives the teacher, the optimizer, the most flexibility to come up with the smartest plan. Second, try to avoid actions like count or display right in the middle of your job. Why? Because now you know that forces an expensive stage break, where all your students have to stop and wait. And finally, use stuff like the Pandas API on Spark. This makes sure the work stays spread out among all the students, instead of accidentally forcing the poor teacher to do all the work alone on the driver node.
So here's my challenge to you. The next time you sit down to write a Spark job, don't just think about abstract stuff like memory and CPU. I want you to think about our classroom. Ask yourself, am I giving my students clear, simple instructions they can do on their own, or am I making them stop and shuffle papers and coordinate for no good reason? Thinking this way, it's a game changer. It's a powerful way to make your jobs run so much faster.